Hello, ladies and gentlemen, and welcome back. We're going to be finishing off the 2018, not Euclid, Fryer contest in this video with question number 4 here. A Bauman number is a positive integer, each of whose digits is 1 or 2. Each Bauman number consists of blocks of digits. Each block contains at least one digit and includes all of the consecutive equal digits. Okay. For example, I think a block has to all be the same of consecutive equal digits. Yeah, sorry. I was misreading that. I know I understand intuitively what they mean by block. It's always weird when you see some obvious thing put into words. But okay, here we go. So we've got a block of 4 2s, 5 1s, 1 2, and 3 1s. This is a 13-digit Bauman number, and they go on to, I guess, detail the blocks. Here we've got 7 2s. It's a 7-digit number, Bauman number, consisting of a single block of 7 2s. Okay. So it's just a bunch of 2s followed by a bunch of 1s, followed by a bunch of 2s, followed by a bunch of 1s. So, I mean, really any number that just has 2s and 1s is a Bauman number. It's up to us to later block it all out, but yeah, just 2s and 1s, that's all it is. I don't think 2s and 1s are actually that important. So maybe this is secretly sort of a binary word question. I haven't actually finished reading it, but we might end up thinking of this as 0s and 1s, and there might be some computer science in here. I don't know. Anyways, let's actually get back to it and read through the question, shall we? So we've got 4 parts, 2 light bulbs and 2 written, and I think as I mentioned in question 3, it's probably 2 2 3 3 if you're looking for a mark breakdown to try and focus yourself and get the best score possible. So light bulb A here. How many 3-digit Bauman numbers are there? Well, Bauman number can be, so we need, maybe the reason they didn't use 0s and 1s is because they didn't want to worry about leading zeros. We need 3 digits. Each digit can be a 1 or a 2. So 2 choices per digit. And we've got 3 choices to make. As to say, if we imagine a 3-digit number, there's 2 possibilities for this number, 2 for this number, and 2 for this number, and we just multiply them all together for an answer of 8. You could also say 2 to the 3. That's where these 3 choices and 2 choices per digit. Actually, just so we're not confused on the word choices, 3 digits to make. Let's say. Okay, if there was a 10-digit Bauman number and we didn't care about blocks, because it doesn't look like we care about blocks yet, there'd be 2 to the 10 possible numbers. Okay, 2 choices per digit, and they don't seem to be affecting each other. Now, as soon as we start talking about number of blocks, you know, if they say I specifically want a block of 1 1s in the middle, then that starts affecting choices and things like that. But right now, it just seems like it's free choice. Okay, so 8's our answer for 4A. How about 4B? How many 10-digit Bauman numbers consist of fewer than 3 blocks? So fewer than 3, that means less than 3. So that's 1 or 2 blocks. So I suspect this will just be some casework. So fewer than 3 means we only have 1 or 2 blocks. So we'll do one case. Just having 1 block. Well, that's going to be 10 1s or 10 2s. So this is two possibilities. So we've got 2 numbers. This is 2 possible Bauman numbers. So 2 numbers come from just having 1 block. How about 2 blocks? Now 2 blocks is a little more interesting. So for 2 blocks, if we're going to count these, we have some choices. So we're going to have a block of 1s and a block of 2s, or a block of 2s and a block of 1s. Now we know it's got to be 10 digits overall, so we could say k 1s, and then how many 2s would we have? Well, we'd have 10 minus k 2s. And for the exact same reason, we could have k 1s, or sorry, k 2s, and then 10 minus k 1s. Okay, so we can sort of do our counting at the same time for both of these. So, how many, once I've chosen k, that's it. Right? As soon as I choose k and which block type is going first, we're done. We don't have to think about this anymore. That determines our number. So we've got two choices. 1 or 2 go first. Times how many choices for k. So k could be 1, 2, 3, all the way up to 9. You can't have k is 10. Right? Because if you have k is 10, then that would mean that there are 10 minus 10 2s, and that would be 0 2s, and that wouldn't be 2 blocks. That would be 1 block. Well, I suppose you could say, let k be 10, but then you don't want to count this case. So just be careful you're not double counting. That's a serious problem that can happen. So we've got 9 choices for k. So that's 18 possibilities. So 18 plus 2. This is going to be 20 Bauman numbers. And 20 is going to be our final answer for this one. Okay. So now we've got C and D left to look at, and these should be a little harder, and we actually have to write up our solution, so we're going to have to be a little careful, especially if there's more casework. So for C, determine the number of Bauman numbers that consist of at most 3 blocks. So that means less than or equal to 3. So we could have 3 blocks, and have the property that the sum of the digits is 7. Okay. So we're not restricting the number of digits we can have, unlike the first 2 questions, but we are restricting the number of blocks we can have, just like B part. So once again, we might start off by saying, well, we might actually use the English that they use. At most 3 means 1, 2, or 3 blocks. Okay? So let's go through this case by case, I guess. So suppose we just have 1 block. Well, we could have K1s or K2s. So that would be a single block. Now, the sum of the digits, well, this one would be K times 1, but this one here would be K times 2. Well, if 7 is K times 1, then that means K is 7. But if 7 is K times 2, that would mean that K is 7 over 2. Well, that can't happen. So the only number in this situation with 1 block that works is a block of 7 1s. But there we go, that's 1 number. Okay, how about 2 blocks? Well, again, very similar reasoning to the last one. We're going to have 1s followed by 2s or 2s followed by 1s. There's going to be some symmetry here. So case 2 blocks. K1s followed by, let's say, M2s. And so the sum of the digits is K times 1 plus M times 2. But both K and M have to be greater than 0. So we got to be aware of that. Well, let's see. We could have 1, 2, and that would leave 5 1s. Or we could have 2 2s, and that would leave 3 1s. Or we could have 3 2s, and that would leave 1 1. So each of these is a Bauman number. So we could have 1 1, 1 1, 1, 2 2. They didn't actually ask me to, oops, sorry, just 1 2. They didn't ask me to write them all out, but I feel like it's just easy to do that. And you don't have to write out the other side, but do not forget that similarly you can have K2s followed by M1s. And that'll lead to just the mirror image. So this is 6 Bauman numbers. So we have 1, we have 6. And now, I suspect the longer case, how about 3 blocks? Okay. So we can either have 1s, let's say K1s, M2s, and L, let's say N. The time to use L was a while ago. N1s. Okay, now we need K, M, and N to be positive, otherwise you don't actually have a block. You have one of the previous cases. So 7 still needs to be the sum. So this is K times 1 plus M times 2 plus N times 1. Once again, we can make a little chart. We could have M is 1, 2, or 3. So K plus N is, so this is 2M plus K plus N. We'd have K plus N is 5, or 3, or 1. And so we could have pairs KN, and that would be, well, we can't have 5 and 0. We could have 4 ones, a 1, 2, and then a 1. We could have 3 and 2. We could have 2 and 3. We could have 1 and 4. That's it in terms of possibilities. We could have 2 and 1, 1 and 2 for the 3s, and you can't have anything for the 1 because that would be 1K and 0, and N is 0, and that would mean you don't actually have a block at the end there. So each of these gives me Bauman numbers. So 1, 2, 3, 4, 2, 1, 1, 2, 3, 2, 1, 1, 1, 1, 2, 1, 1, 1. Basically, we're just looking at this first example and shifting the 2 in here, and that's really all that's happening. We could have 1, 2, 1, 1, 1. And so that's one set, and then we could also have 1, 1, 2, 2, 1, or 1, 2, 2, 1, 1. So that's 6 more. And then we could also have, and here's where it gets a little more interesting, we could also have K2s, M1s, or N2s, and N2s. So 7 needs to be K plus N times 2 plus M, and we need K, M, and N to be greater than 0. Fine. So what could we have? Well, we'll focus on the single right now. So M could be, and we just learned about this, we could have 5, 3, or 1. That would leave K plus N is 1, 2, or 3. And what are the possible pairs KN? Well, there's nothing for this one, because that's this first situation, and you can't split that block of 1, 2 into 2 blocks by putting 1s in between them. There aren't any 2s to be split between. Or aren't enough 2s, I guess. We could have 1, 1, and that's it. So that would equate to 2, 1, 1, 1, 2. That's really the only 3-block Bauman number that starts with a 2 and it has the digits add to 7. And then we could have 2, 1, 1, 2. So that's 2, 2, 1, 2, or 2, 1, 2, 2. So that's 3 more, and we had 6 more over here. And that's our last case. So we've got 1, 6, 6, that's 13, plus 3 is 14. So 14 Bauman numbers satisfy the conditions. So for a question like that, you just have to be very careful. Know what your cases are and then go through them slowly. Don't try to speed things up, and make sure you actually did write the things out. A good suggestion, like when you're trying to write them out to verify them, do them in some sort of order. I mean, here the CADE value is decreasing, so that's one way to do it. But just make sure, and then when you go to add them all up, and I've had this happen in the past, I miss one. That's why I chose to use blue color so it would stand out at me. Okay, we are not done yet, though. We've still got D part. Some Bauman numbers include a block of exactly 2018 twos. So if it's exactly, that's kind of interesting. So you'd have 2, 2, keep going on for 2. But you can't, like, once you've reached your 2018, you couldn't follow that up with another 2, so it would have to be like a 1. There'd be 1s on either side to ensure that it is exactly the number that we have said. Okay. Determine the number of 4,037 digit numbers, digit Bauman numbers, that include at least one block of exactly 2018 twos. So you could have more than one, and with 4,037, you can have one that has more than one. You could have twos, 2018 twos. A 1 would put you up to 2019, and then another 2018 twos would get you all the way to 4,037. So that one is allowed. It's not exactly one block, it's at least one block of exactly 2018. Okay. So, knowing that... Whoops. Wrong button. Knowing that we have at least one block of 2018, it's probably a good idea to, as we try and count this up, might ask, where will our block... There could be more than one, but really that's the only case where you're going to have more than one block. Where will our blocks of 2018 twos go? And what I mean by that is, do we start off with 2018 twos, and then you'll need to have a 1, followed by who cares? Because we need to ensure there is the 2018 twos. So could it go there? So this would be at the start. Or it could be at the end. So it'd have to be preceded by a 1, and then it doesn't matter. So let's say 1s and 2s. 1s and 2s. Or could it go somewhere in the middle? So you'll have 2018 twos, but since it's somewhere in the middle, you'll have on either side some 1s, and then 1s and 2s. We don't actually care about the block structure for the rest. Okay, so this is, again, going to give us 3 separate cases. Okay, the first and the second cases, first and last cases are sort of just going to be mirror images of each other. Maybe we'll exploit that, I don't know. Okay. So, I'm trying to think. I already know that there's going to be one, at least the way I was going to write this up, there's going to be one number that appears on 2 lists, and that is the definition of double counting. Counting the same thing twice under sort of 2 different headings, or under 2 different lists. And that's the whole bunch of 2s, a 1, whole bunch of 2s, because that has the 2s, a block of 2s at the start that we're interested in, but it also has a block of 2s at the end that we're interested in, and so it would be counted in the sort of the first case, but it would also be counted in the second case, and we don't want to do that. So, I guess maybe to start writing this off, we should address that and determine, really, will other situations like that arise? So, notice that for a 4,037 digit number, there are at most 4,037 over 218, a little bit more than 2. blocks of 2018 twos that can happen. I might say something like the only number with two 2018 twos blocks is a whole bunch of twos, a 1, a whole bunch of twos, as we need at least 1, 1 to separate the blocks. And 2018 plus 1 plus 2018 is 4037. So that guy's covered for both of them. So that's a situation. So what about so for any other numbers, we'll have just one block of 2018 twos. So here's our case, 2018 twos right at the start, a 1, and then 1s and 2s. Incidentally, let's say this guy he's one number. We found one that works. Okay, so I might say the first 2019 digits are fixed. You could again point out that we need that 1 there, otherwise you might get 2019 twos, which isn't allowed. So, but the rest can vary. As long as they aren't all twos. And so, getting back to choices, we've got this is 2018 digits, each with 2 choices. So that's 2 to the 2018 minus 1, the all twos case, which has already been dealt with. Possibilities. And since we've got our block of 2018, and all of these are guaranteed to be Bauman numbers, these count. So just for my future count, there we go. 2 to the 2018 minus 1. Same sort of situation is going to happen with the end. So why don't we do that case right now? So 1s and 2s. A 1 and 2018 2s. And we don't have to write everything up again, but we can just say similarly, any choices for first 2018 digits except the all twos case will work, and importantly produce different numbers. Don't want any more double counting. So this is, I'm just going to write the possibilities so I don't have to change color too much. 2 to the 2018, again, minus 1. Why is that minus 1 there? Because there is one of the possibilities where all of these numbers are 2s, but that's already been counted. Not by the previous case, but by the situation where we looked at having exactly 2 of the satisfying blocks. Okay. So now the last case, we'll get another piece of paper for that. So 1s and 2s, a 1, 2018 2s, and a 1, and then 1s and 2s. So we've got a bit more going on here. the middle, I'm going to put middle in air quotes just because it's not the exact middle, but the middle 2020 numbers are fixed. This leaves 4,037 minus 2020, 2017 digits to choose. 2 choices apiece, and there won't be any overlap. With previous cases. So that would be 2 to the 2017, but we have something kind of critical. Okay. Where is our giant block of 2018 twos? And you might say, well, it's somewhere in the middle. Yeah, but where? Okay. So we know what it's like if it's right at the start. We know what it's like if it's right at the end. But is it just shifted one? Does it start on the second digit, on the third digit, on the fourth digit? You know, is it 1, 2, 2, 1, and then my 2018 twos? Where does this giant block occur? Okay. So what are our choices? Well, it can't be at the start, so it can't be at the first position, and it also can't end at the end. And that, you know, so where do we exactly place this? Well, I think the easiest thing to do in terms of placing it is ask, where is the first 2 in our giant block going to be? Can't be in position 1. It could be in position 2 or 3 or 4. How many possibilities? So we still have to count for that. So we might say this gives 2 to the 2017 possibilities per position of 1 followed by the 2018 twos followed by a 1. Okay. So we ask how many positions are there? So we'd have the first, the second, the third position. So we'll say where is the first 2 in the big block placed. I haven't given myself enough room. So position 1, position 2, position 3. All the way down to 4037. Well, it can't be in position 1. It can be 2 or 3, all the way up to, now there's going to be some middle point where you can put the 2s and they keep going, and then there's still enough room here for a 1. So that would be a 1 there. And so the last 2 in my block would be in the 4036th position. And so, if it were just a block of 2, then I'd be allowed to have 4035 as a leading position. So that would be a block of 2, subtract. So, latest it can go is position 4037 minus 2018, right? Because if it was just a block of 2, the one if I push it to the farthest right it could possibly go, the 1 would have to go in 4037, and then that leading 2 would be in position 4035. And how do we, with a block of 2, how do we obtain that position from 4037? Subtract 2. And so we could say, since the 2 is followed by 2017 twos and a 1. If it's not followed by a 1, then we could have a bigger block of 2s, or these guys might be at the end. All cases we've dealt with. So from 2 to 4037 minus 2018, which is 2019. So all these positions are valid, so how do we figure out from 2 to 2019 inclusive is 2019 minus 2 plus 1, and that is 2018. So we've got this many choices of position, 2018. So this gives 2018 for the number of positions that middle block can go in, and then 2 to the 2017 for all the various other choices of 1s and 2s outside of that middle section. So our total is one block that contains 2, 2 ways to fill this in that have just one block, and the block is either at the start or the end. I want to make sure they were 2018s. Yep. And then finally, 2018, not 28. 2018 times 2 to the 2017 Bauman numbers. Is it 2 ends? I feel like it was 2 ends. Nope, just 1 end. Okay. So that many Bauman numbers. Now we can clean this up a little bit. 1 cancel out, and then we could take out a 2 to the 2017. So that'd be 2 plus 2 plus 2018 minus 1. You know, it's entirely your choice how far you want to go. That'd be 2022 minus 1. I guess we could take out at least one other factor. Yeah, just one factor of 2. Yeah, certainly you can't write this out with a calculator, but I guess this is probably the shortest expression of the answer. But, you know, leaving it like this, as long as you've clearly explained where these come from, without these crosses, incidentally, is going to be a perfectly fine answer as well. Okay? They didn't tell us to put it in a specific form, so as long as our final answer is clear, relatively simple, and based quite clearly off the work that we've done earlier, they're not going to nitpick about, oh, this wasn't the simplest possible of all the infinite ways to express this number. They're going to give you the mark. Okay? As long as it's quite clear, and we can see where the 1 and the plus 2 to the 2018 minus 1, and we can see where all that came from. But, you know, if you got time, clean it up a little bit. And there might even be a slightly cleaner expression than the last one that I finished off with at the end. That's okay. But that does it. That finishes off question number 4. So our whole Friar contest is done at this point. So up next will be the 2018 Galois. If you're interested in that, it's a grade 10 level paper, a little harder, just based on grade level. Of course, I do have many other Friars, or if you want to, you can take a look for the Pascal papers. Those are multiple choice contests, still also aimed at grade 9. You can take a look at. Okay? So feel free to root around for those. Feel free to leave a comment if you had different ways of doing the questions. Feel free to subscribe if you want to be kept up to date to the contests that I'm putting up. But other than that, have yourself a wonderful day, and keep on enjoying math and math contests, eh?